So let's quickly recall the notions we introduced last time. There are quite a lot of them. So it's good to see it again. Lecture 24. So some of the key ones, let's go through them again. Previously. The first one is, of course, we need to recall what is a regular partition. So a partition is regular. You have somewhere some exceptional set V0, V1, V2, Vr. So this is a regular partition with some epsilon parameter. If it satisfies that, I will just write the most important one. If all but epsilon r square pairs are regular. This is the most important one. Epsilon regular. And what does it mean, epsilon regular? So if we look at 2 and r, that just means when you take a not so small subset of it, at least epsilon fraction, then the edge density between these subset is more or less the same as the original one. So this just means for any, let's say this is x, x2, xr, right? For any xi in vi, let's say vi vj is regular, and xj in vj with size at least epsilon size, then the density between xi, xj, meaning the number of edges between xi, xj, normalized by xi times xj, is, let me write it this way, equals to the density of vi vj plus minus epsilon. Same thing, right? So up to a plus minus epsilon, density of large subsets are the same as the original one. And this seemingly simple looking condition, it's quite pseudo-random. In particular, implies that between any two regular pairs, apart from some tiny bit of bad vertices, most of the vertices, the typical vertex, they have the correct degree. If the density is d, then you have d times vj degree to the other side, plus minus some error term, plus minus epsilon vj. This is one of the consequences we saw last time. And regularity lemma is saying every graph, for every graph G, there exists a regular partition with the parameters I'm skipping here. The important thing is that, the most important thing is that the number of parts is bounded, independent of the number of vertices of G. So we can often reduce some extremal problem from G. Remember this reduction. We can reduce a problem A on some graph G to some problem B on this reduced graph. R. So today we're gonna make this rigorous by seeing this embedding lemma. We've seen one such example last time. The example is Erdős-Shimonovich that extremal number of general graph is 1 minus 1 over chi of h minus 1 plus little o1 times n squared over 2. When we prove this, we basically say in G is H free. Then when you reduce to this bounded graph R, we can get a stronger property that it's K chi of H free. We know that it does not contain any homomorphic image of H. In particular, the complete graph on chi of H number of vertices is a homomorphic image of G. Then we can use Turan's theorem to solve R, which then reflect back to the edge density of G. So what is this reduced graph? The reduced graph is defined based on the regular partition. So technically speaking, R is, it depends on the partition we have. So the partition, for example, looks like V of G equals to some exceptional sets, V1, VR. So what we're gonna do is, we're gonna shrink each one of these to a single vertex. Why we can do that? Because usually when applying regularity lemma, we're gonna impose also a lower bound on the number of parts we need. This is the little m in the statement we have last time. Since there are so many parts, the fraction of edges inside this cluster is negligible. So we can shrink it into a single vertex and only cared about the majority of the edges, which are those going across different VI, Vj. Now, we can also forget about the pairs that are irregular. There are not so many of them. Epsilon r squared, negligible. So we don't care about irregular pairs. We also don't care about sparse pairs. If they are very sparse, there's not so many edges in between them. It could be completely empty between some VI, Vj. So we also discard all those edges between sparse pairs. In other words, we're gonna just utilize the pairs that are regular and dense. It has some density bounded from below by some constant that's larger than epsilon. Let's say 10 epsilon, that's usually enough. And the reduced graph is defined after shrink to a vertex. You put an edge between two indices, two parts, if and only if it's regular and dense. So you usually have some parameter, epsilon and delta. Delta is bigger. And so this R technically, well, of course, depends on epsilon and delta, and also depends on if this P is the regularity partition. It also depends on this P, right? To be precise. So this is the graph where V of R, we don't care about V0, and you shrink this to a vertex. Let's just call it 1. Let's just call it R for each one of them. So we have vertex, the first R integer, and I is adjacent to J if and only if the corresponding parts, the pair, is both epsilon regular. We have this notation last time, is epsilon delta regular, meaning it's epsilon regular, and the density dvivj is bigger than delta. Remember? Good. So we can now state this embedding lemma. Before stating the embedding lemma, let me rephrase this thing. So one of the things, embedding lemma is basically saying this thing. Okay, we can so a key property is that if G is H-free, then it implies that the reduced graph R is H home free, meaning it does not have any homomorphic image of H. So let's rephrase this. How do we rephrase this? Well, let's rephrase its contrapositive. If you look at the contrapositive, it just means if R contains, so you negate this, implies a negation of this, right? So the contrapositive will be if R contains a homomorphic image of H, then G contains a copy of H. That's the contrapositive. Let's rephrase it again. What does it mean having a, what does this mean? This condition is the same as H is contained in the blow-up of S. Recall, this graph blow-up is obtained by replacing each vertex V by an independent set IV of size S, and each edge UV by complete bipartite graph between the corresponding independent sets blow up IU IV. Okay, very simple. We've seen this before. So if you have, say, diamond, you blow it up, each one to S vertices. You put all edges in between whenever there was an edge before in the corresponding between the corresponding vertices. Right? So if you contains a homomorphic image of H, this is the same thing as saying H is contained in the blow-up of RS. Because what it means to have a homomorphic image means there is a homomorphism. This is the same as, is this the homomorphism phi from H to R? And some vertices of H, might not be injective, but it preserves the adjacency of edges. It might get mapped to the same vertex, but since we now blow it up, H can be, we can make this map injective since we have many copies now. So we can obtain a copy, the blow up of R. we're going to phrase the embedding lemma in this way. All right. Here comes the embedding lemma. For any d between 0 and 1, and you have some delta natural number. Okay. Natural number. This will be the maximum degree of delta of h, the graph we want to embed in G. There exists epsilon 0 such that the following holds for all epsilon less than epsilon 0. Let G and H be graphs with, so first of all, the maximum degree of H is bounded by delta. And then we also take some natural number S, and let R be a reduced graph of G. So what does this sentence mean? This means we first apply regularity lemma on G to obtain the epsilon regular partition, and then we only make an edge between two indices whenever they are epsilon regular and density D. Obtain this reduced graph R. Now we suppose each part of the regular partition has size. So we have this VI, right? VI has size, let's say L, which is bigger than 2s over d to the delta. Then we have the conclusion that this is the conclusion. Then if H is contained in Rs, in other words, if R contains a homomorphic image of H, then G contains an actual copy of H. So one can see this embedding lemma. There are several remarks. The remarks is from G originally it's H freeness. We bootstrap it to a stronger condition. We reduce it to the problem to the reduced graph, right? But this reduced graph has a stronger property. It does not even contain homomorphic image of H, not just H free. Remark. The important remark is that here H need not be of bounded size. So we can here H need not be of bounded order. We can embed bounded. We can embed as long as the maximum degree of H is bounded. Bounded degree graphs of order up to linear size. Linear size means big omega of n. So to see this, let's look at this parameter. We have n is the host graph, the number of vertices, right? Which equals more or less, if you pretend V0 is empty, you have R parts in the partition. Each part is of size L, right? So this order is roughly R times L. But remember, R is bounded constant, it's absolute constant, not growing with n. So as n tends to infinity, L must grow at the same rate as n. In other words, because R is bounded constant, so we have n and L, they grow the same way. Well, let me write it this way. Each part is linear size in n. That we already know. And here, H is of order what? Could be taken as order linear in S, basically. Right? H could be as large as order S. And S and L, they are linear. S could be as large as L if this is constant, and this is also constant. Everything here is constant. Which is the same as S could be linear in L, which is linear in N, right? We're going to make use of this remark later for a Ramsey type statement. Okay. All right. So let's give a proof, a sketch of the proof. Of this statement. We want to prove this. It's basically a greedy embedding. And then make use of the fact that most of the vertices between every pair of regular dense clusters parts, typical vertex has the correct degree to the other side. That's one of the lemma we proved last time. And then we can always do this greedy process and always zoom into the eligible vertices to embed. So let me maybe give an example of a simpler case that for generic H, the proof is not much harder. So for the concreteness, let me first sketch the proof in a simpler case that R is just nothing but a triangle. Okay, and our H is this diamond, but I'm gonna draw it like this. And H is contained in the blow-up of R is obvious here because the homomorphism basically looks like this. You map these two red vertices to this red vertex of R. You map this guy to here, and you map this guy to here. Okay, so this is our homomorphism phi. This is our homomorphism, and let's recall what does the graph look like. Actually, let me move these things a little bit more to the center. And let's recall in the graph G, in G, how can we have this triangle in the reduced graph R? That means in G, we have three clusters, three parts. If this is, let's say, IJK, you have VI, VJ, VK that are pairwise regular and dense. So epsilon delta regular, right? Good. So now our goal is to embed this guy, H, in between these three clusters. All right. You can just take an arbitrary order of the vertices of H. Let's say we can take, let me use a different symbol, x1, x2, x3, x4. I really take an arbitrary order. So let's take this order. So we're gonna, now we're gonna embed these vertices, x1, x2, x3, x4 in this order. First embed x1. And how are we gonna embed x1? We first look at this homomorphism, and we see that x1 is mapped to the vertex I in R under this homomorphism. So we're going to embed x1 to the corresponding parts Vi. But we're not going to just embed it to any arbitrary vertex of Vi. Think about it. Even though this is nice and pseudo-random, it could very well be that there's a vertex in Vi that's bad. It has no neighbor at all to Vi, Vj. We just know that there are very few of them. So we need to exclude the first step. We want to embed x1 to Vi. We first scoop out some bad vertices. We know there are at most epsilon fraction of them. That's bad towards Vk. Has the round degree to Vk. But there's also some have the round degree to Vj. So you delete those. Okay, you delete two portions. Now the remaining vertex, all vertices here has the correct degree. Okay, to be precise, let's say I use y1. We will map xi to yi in G. Okay, this is in H. So we map x1 to y1. And y1 is nice in the sense that the degree to this side is the correct degree. To this side, also the correct degree. Okay. 1 second. No, that's fine. Yeah, it's okay. So after we do this step, mapping x1 to y1, we need to do some update. What do I mean by that? After we map x1 to y1, we put restrictions on vi and vj and vk. Why? Because we're going to map x3. We know that x3 under phi is going to be mapped to vk. To visualize it better, let me maybe draw vk like this, correspond to this blue dot. Draw vj like this, correspond to the yellow one, and this one is here. Very good. Okay, so we know that we're going to map x3 to the blue part and x4 to the yellow part under phi, because of phi. And since we already map x1 to y1, and since x3 and x4, they are adjacent, they are neighbors of x1, meaning that the y3 image of x3 must lie in the neighborhood of x1, and so is x4. In other words, we need to update vk by the neighborhood of y1. And x3 can only be embedded now inside this neighborhood. But the good thing is we choose y1 as a typical vertex. So this guy is large. This is at least delta minus epsilon times vk, right? Same thing here. Good. This is what I mean by update. After we update it, good, we're going to move on to x2. So now we have to choose y2 to embed x2. But we cannot choose any arbitrary one, because even though we scoop out those bad vertices, and every vertex outside these parts is good with respect to the original cluster. Now we've already updated this cluster. We update it by the neighborhood of y1. In other words, we have to update vi as well. So remember another lemma, the slicing lemma, saying if vi vk is regular, then this part vi, excluding the bad vertices, and this large part is large because of this. So we need to take delta to be at least 2 epsilon. So this take up to at least epsilon fraction, right? So this part is also regular, although the regular parameter is slightly weaker. What it means is that most of the vertices inside here has the correct degree to these two parts. So you can scoop out some bad vertices once again. You do some updating one more time. You scoop out some bad ones with respect to these two blue parts. Now you can embed y2. Let's say I embed it here. And the rest you can already guess. We have y2 having the correct degree to these parts. We're going to update them again. And update this part again. What's this size? This size is going to be delta, right? I use delta times delta minus epsilon minus epsilon, correct? Times fraction. Okay. Very good. So what have we done? We embed x1 and x2. And now we update Vj and Vk to this green pair such that all vertices in this green pair, they are co-neighbors of x1, x2. So whatever you choose there, it's going to be fine. It can be x3 and x4. They are linked to x1 and x2. All you need to do is to choose one so that x3 and x4, you just need a single edge in between this green part now. And that's also easy because this fraction, we choose delta large enough so that this is still bigger than epsilon. If this is still bigger than epsilon, then that means by the definition of epsilon regular pair, the density between this green pair and the density between the large pair are the same, up to plus minus epsilon. So that means there are lots of edges in between this green pair. Finishing the proof, you can embed x3 and x4 to be the endpoints of some edging here. All right, so here, let me summarize what I just said through this concrete example on the left. So given d delta, we will choose epsilon 0 less than d such that it satisfies this condition. And this condition inequality is to just make sure that not just for this graph, diamond graph H, for any generic graph H with bounded degree delta, after you do this one step at a time according to the homomorphism embedding greedily, and every time you zoom in and update the cluster, you get smaller and smaller fraction, right? And we want to make sure that no matter how small the fraction it gets, eventually it will be at least this large, which is still at least the epsilon fraction. So we can make sure that the large bit, at every single step when you do the update, these parts, new parts, you update it to still epsilon large. Now, and we have this homomorphism. Let phi be a homomorphism from H to R is the homomorphism. And we can order the vertices. We're going to embed order V of H as x1 to xh, right? And we're going to embed x1, xi minus 1 to the top, 1 by 1. Initially, we're going to set yj to be vj. And this yj is the eligible vertices for this little y, the image of xi, to go to. This is the set of eligible vertices in Vj for xj to map to. initially you set everything to be eligible. Right, so we're going to embed it one by one. So maybe I should move this sentence down here. Yeah. Embed this one by one and update eligible vertices. Update, how do I write it? The sets of so we're going to update. Let me write it first. So you embed one by one, and suppose at this step you embed the I-1's vertex. So here I embed Y1 X1 vertex. Then you need to look at all the indices after X1 that's adjacent to X1. So we skip X2 and look at X3 and X4. You look at all the indices after I-1 that are adjacent to this last vertex we embedded. For all these ones, you need to do the updating. You need to zoom in. You need to update it. How to update it? By update this Y phi xj update to you need to intersect it with the neighborhood of the I-1's vertex. Oh, actually, I should probably write yi-1, right? We map these to yi-1, map to this to y1. Okay. Maintaining always, we need to always make sure this updated set is at least epsilon fraction of the original thing. No, I think I'm confusing. No, that's correct. Maintaining always that this eligible set is at least epsilon fraction. Okay, and at the end, when embedding, the next vertex to embed is xi, right? We embed xi-1. So when embedding xi, where does xi goes to? It goes to phi xi's part, the corresponding eligible sets. In y phi xi, then we just need to notice that for every j bigger than I with xi, xj, and h. Then this is inside V of Vxi. In V of Vxi, now what I'm writing is we need to also scoop out these bad vertices with respect to this updated set. Okay? But we know this bad vertices is negligible. In this set, all but epsilon fraction vertices have degree, the correct degree. Degree, how much? What is it? At least d minus epsilon times y v u xj. Let me think. Do we need to update the regularity? Zoom in. And no, yes. Just the lemma we saw last time. Okay. Remember, this is the set B inside this Vj. For all but tiny fractional vertices, typical vertex has the correct degree to B. And think about this B as y phi xj, last time's lemma. Now we have what? As Vi d minus epsilon. So what has this achieved? This is saying that every time when you embed xi vertex, the eligible vertex is shrink by at most d minus epsilon. So if you shrink by d minus epsilon delta times, because every vertex is adjacent to delta vertices in H, you also have to minus epsilon times delta Vi. This is for every cluster, if you embed it, you have to scoop out some exceptional vertices that has wrong degree to your neighborhood cluster. There are delta such neighborhoods. Each time you scoop out epsilon to have the typical vertex. If eventually this is larger than epsilon fraction of Vi, this process can continue forever. We don't get stuck. Okay, here's the proof. This is more technical, the proof, but I want you to remember this example. All right. With a little bit effort, we can prove something's even better, which is the counting lemma. Here, as you can see, after we scoop out vertices that are atypical, we just embed the arbitrary, we just choose arbitrary y1 to be the image of x1. You see here, the choice for x1 is almost everything. And the choice for y2 is also a lot. x3, x4, also a lot. So we can get a counting version. Not only we get a copy of H in G, we get many, many copies of H in G. This is the next property we're going to see about reduced graph. If you view reduced graph as a weighted graph, where the weights of the edges are the density between corresponding clusters, then the weighted count of subgraph density H is the same as the H density in G. This is the counting lemma. The next important lemma. Counting lemma states that a weighted reduced graph preserves if I spell it wrong, S-E-R-V-E, I think, right? Let me check. S-E-R, yes, S-E-R-V, preserves subgraph densities. The reduced graph as a weighted graph has the same subgraph statistic, density statistic as the original graph. And here, what do I mean? If you take, again, triangle as example, if this is my weighted graph, if the weight here is 1/3, 1/2, 1/4, then the number of triangles here, how many triangles? Number of triangles is 1/24 in R, right? Then if you look at in G, how many triangles? G is kind of like a random blow up. If you view G as a random blow up of R, then you pick 3 vertices from G. The probability that you form an edge here is 1/3 because that's the density there. It's a regular pair, so it's random-like. The probability that these two form an edge is 1/2. The probability this form an edge is 1/4. So altogether, you get a triangle with probability 1/24. So if you look at this kind of canonical triangles with one vertex in each part, the density of this triangle is exactly 1/24. It's the same as the weighted count in R. So the weighted number of triangles here is 1/24 times, let's say, what's the size? If this is m cubed, at least this much in between 3 different parts. And counting lemma is saying that this is true not just for triangle, for any bounded degree, bounded size graph H. Even this graph H we want to count. And let's say we have V1, V2, VH are the clusters of G on which, between which we're going to embed our H with, let's say H has H vertices. Each VI has size little n. All pairs VI, VJ are epsilon regular. And dVi, Vj, the density Dij is Dij, which is much bigger than epsilon. Here by much bigger, it just means much bigger than some, larger than some constant times epsilon. Then conclusion is that the number of canonical copies of H. This just means canonical means what? This means if this H, the vertices, is little v1 to little vh, then the copy, we need to require vi to be capital Vi for all I in H. Okay? This is what it means. We don't want to embed triangle like this. We want each vertex goes to its own part. Okay, the number of canonical copies of H in V1 at the top to VH is the product Bij minus plus some constant times epsilon NH Ij is an edge of H for some C absolute constant depending on H. This is the counting lemma. Exactly what I said here for the triangle case. If you forget about this error term and forget about the large graph, okay, forget about G at the moment, just look at if you think of Vi to Vh as a regular partition and you build now a reduced graph 1, 2 to H, since every pair is regular, density Dij, so this is a complete graph on H vertices with weights Dij between I and J. What's the count of H? Okay. I think I should say at least, all right? And maybe put a minus here. You actually have the correct count, also upper bound. Here, simply because if H is a complete graph, you have the correct count. I have equality plus minus, but H might not be a but if I require this, that's fine. You can have equality. I was worried about the automorphism of H. But for us, lower bound is enough. We have the counting. Once again, if we require each Vi actually goes to capital Vi, then we have equality here. All right. Right. The proof of this is not much harder than the embedding lemma proof we just see. I'll leave it as exercise for you to prove it. Simply as I said, here we just choose Y1 as a typical vertex. You have many choice of things to choose for Y1. So is any other vertex. Every time when you zoom in, you only lose some error term. The majority term remains. This is the little Dij between different ij. The exercise for you to prove, you just need to prove it for the triangle case. All right, so, oops. Exercise. Proof the counting lemma for the triangle case. And the next one, slightly more challenging, is there's also an induced version of the counting lemma where we can count, for example, induced copy of 4 cycle. You require these 2 edges cannot be there. So try to think how you can formulate an induced version and prove it. Formulate and prove a counting version, counting lemma for induced C4 full cycle. Okay. Now we can see application of embedding lemma. This application is a problem in Ramsey-Turan theory. One of the early applications of regularity lemma. So what is a Ramsey-Turan problem? Recall in the Turan problem, in Turan's theorem, let's say your KT free graph. What's the size? It's the number of edges in this complete multipartite graph on t minus 1 parts. This is the t minus 1n Turan graph on t minus 1 parts. So this maximizer, let me write it again. This is the maximum number of edges of an m vertex graph G, which is H3. But this maximizer here in particular, it's very highly structured. So in particular, it has a large independent set. It has an independent set of size linear in n, if t is a constant. Schorsch in the late 60s asking if we want to consider this Turan problem, but with the host graph G not having linear size independent sets, how much we're going to affect the maximizer, the maximum density. This is Ramsey-Turan problem. So apart from being H3, we also require alpha G to be small than some parameter m. So here's the definition. The Ramsey-Turan number denoted by RT and H M, as I said, is the maximum E of G, where G is m vertices, alpha G, m most m, and G is H3. Okay. Now, the most classical case, which is the case we're going to look at, is when m is little o of n. So we do not require linear size independent sets. So here the little o n is quite informal. Let's define it rigorously. How do we define RTNH little o of n? Formally, definition, we're going to define Ramsey-Turan density which I denote by rho of H of a graph H to be. So what do? First, we look at the maximum size of an n vertex H-free graph whose independent set is m most little delta times n. We look at its edge density, so we normalize it by n choose 2. And we look at this edge density behavior as n goes to infinity. This is not hard to see that this limit exists. The edge density limits when we fix the independent set to be no larger than delta fraction of the whole vertex sets. Now you take another limit with delta goes to 0. Take another limit, delta goes to 0. This is the Ramsey-Turan density. And we're going to define RT NH little o n to be this Ramsey-Turan density rho h times n choose 2 plus little o n squared. This is the definition. In other words, this is saying, informally, for any delta, when n large enough, we only consider graphs in which with alpha of g is less than delta n, right? If you, for any linear size sets, for any delta n is linear, on this set of vertices, we must see an edge inside to forbid linear size independent sets. To get familiar with this notation, let's first do the easy case when H is a triangle. So here's a proposition. The Ramsey-Turan number of triangle, recall, Mantel's theorem says when we don't put restriction on the independent sets, we can have n squared over 4 edges. And when we put the restriction, if you don't have, and the maximizers n choose is complete bipartite graph. But if now we say you don't have linear size independent sets, all linear size set, you must see an edge there. Suddenly, you don't have quadratic number of edges. You have little o n square edges. The proof is very simple. I will leave the rigorous proof like this for you. But basically, the idea is for any enough to show the maximum degree of our graph is little o(n). Because then that will imply E of g is at most n times delta of g divided by 2, which is little o(n) squared. And this proof is also simple. Delta of g, look at every vertex v. Its neighborhood, remember the graph is triangle free. We forbid the triangle, meaning that here it's an independent set, the neighborhood of v. Any edge here will give you a triangle. But what do we know about independent sets? Independent set must be sublinear size. It's little o(n) size. So maximum degree is at most independence number, which is little o(n). And we are happy. So triangle case is easy. The thing we're going to look at is the K4 case. For the K4 case, we know this is roughly n squared over 3, right? Plus minus some constants. Depends on the divisibility of n. So the theorem we're going to see is for the K4 case, when you impose, this is by Semerady in 1973. The Ramsey-Turan number for K4, little o(n), is at most n squared over 8 plus little o(n) squared. Before I prove this, let me first remark that this bound is optimal. The Ramsey-Turan density, in other words, remark this is optimal bound. Because later, Bolobash and Erdős provide a matching lower bound construction. So this together implies the Ramsey-Turan density of K4 is 1/4 n squared over 8 normalized by n choose 2. That's the first remark. The second remark is that we don't, in general, we know that for the Turan problem, we have the Turan density determined for every graph h, which is just 1 minus chi of h minus 1. Right? So Erdős-Stone, Szymonovich says the Turan density of a graph, we know it, but there's no such thing for the Ramsey-Turan problem. Open for row h, for general h. The first simplest case that we don't know, surprisingly, open problem, is the Ramsey-Turan number for 2 blow-up of triangle, 2 vertices on each part. You have all edges in between them. This guy, we don't know whether this is a little o(n) squared or it has positive edge density. That we don't know. Now coming back to this upper bound, let's prove it. I will give a sketch of the proof for you to fill in the details. So we want to prove what? You have an n vertex graph, K4 free, independence number, little o(n). You want to show that the number of edges is at most this much. proof sketch. So let's take G, n vertices, K4 free, independence number little o n. Our goal is to show EG is at most n squared over 8 plus little o n squared. Okay. So actually, let me make a remark here on the counting lemma. I want to make this version slightly like this. So the number of copies of H in here with VI in capital VI for all I in H is equals to plus minus. I want to write the equality case. So you want to embed H counting lemma, each vertex to the corresponding parts, if this is regular. Okay. Good. So this in particular implies what? This in particular implies that the counting lemma implies that the weighted number of edges of the weighted graph R is the same up to density, is the same as the edge density of the original graph G. If you think about H as a single edge. Okay. In other words, to prove this, as a weighted graph, so you do the standard thing, you apply regularity lemma, and you let R to be epsilon delta regular. I don't even want to specify these parameters. So this is a reduced graph of G. Do the standard thing, take a regularity partition, R is a corresponding reduced graph. As a weighted graph, the number of edges of the reduced graph is more or less the same as the number of edges of G. Normalize properly. Normalize properly. They have the same edge density. R and G have the same edge density. So our goal is to prove, the new goal because of this is to prove E of R, the reduced graph, is at most R squared over 4. 8 plus little o R squared edges. Okay. This is our new goal. And how do we prove that? It's enough to prove this claim. As a weighted graph, we need to prove two things. One, R is triangle free. There's no triangle in R. Two, as a weighted graph, every edge in R has weight at most 1/2 plus little o1. First of all, let's first see why the claim finishes the proof. This is 1. This is 2. Claim 1 first implies that as a normal graph, not a weighted graph, the number of edges, the number of pairs okay, let me write it this way. Claim 1 implies that as an unweighted graph, the number of edges in R is at most R squared over 4 by Mantel's theorem, because it's triangle free. It has R vertices, triangle free, as an unweighted graph. Mantel's theorem applies. Claim 2, the second part, implies now as a weighted graph, this is your R, right? It's triangle free. So the number of pairs that form in the edge is at most this much. Now each edge, the weight is no more than 1/2. So as a weighted graph, when you count the number of edges, you have to multiply the weight. E of R is at most R squared over 4 times the weight, 1/2 plus little o1, which is precisely what we want. R squared over 8 plus little o R squared. So we just need to prove these two claims. Proof of the claim. Let's look at the first part, why it's triangle free. If you have a triangle in R, basically what I want to say is, if triangle is in R, then K4 is in G, in both cases. We're going to prove this. Triangle in R means what? That means in G, we have 3 clusters. Again, Vi, Vj, Vk, pairwise, regular, and dense. Okay. Then what are we going to do? Pairwise, regular, and dense. Now you can just take some typical vertices. Vi, you take one here, then you update, you take one, you update, you look at the neighborhood, you take another one here, you update the neighborhood here, right? Okay, let me draw it. So this is, let me call it x1. Now I choose some x2 inside, update. Take two typical vertices, x1 in Vi, x2 in Vj, but the neighborhood of x1 such that their co-neighborhood is linear size. That we can guarantee. Okay, this is the co-neighborhood. Linear size means what? This is bigger than independence number of G. That means there is an edge inside. Put an edge inside together with x1, x2. Which plus x1, x2 give you a K4 in G. That's a contradiction. Our graph is K4 free. That's the first part. Second part is very similar. Second part is, if you have a weighted edge in R of weight strictly bigger than 1/2 plus little o1, so that means you have 1/2 plus some c, where c is a constant, right? If you not at most 1/2 plus little o1, suppose otherwise, suppose this is false, so it's bigger than this plus some epsilon constant c. We're going to also embed K4 in G. What does this mean, this weighted edge? It means in the original one, you have some Vi, Vj, where it's dense, and the density is 1/2 plus C. Same thing. We know that there are some vertices that has the bad degree in Vi that has the bad degree to Vj. Scoop those out. Bad vertices with wrong degree to Vj, throw it out at most epsilon fraction. All the rest of vertices have the correct typical degree to the right-hand side. But the remaining, since Vi 1 minus epsilon is linear in N, obviously, which is bigger than independence number of G. So you can find an edge. Is this an edge? Let's call it x1, x2. So we have an edge inside here where the endpoints are typical vertices. What does it mean, typical vertex? That means they have their degree to the other side, the degree of xi in Vj is at least 1/2 plus c minus epsilon times Vj. And let's just say I take epsilon to be c over 2. So this is at least 1/2 plus epsilon times Vj, right? This implies that this size is at least epsilon Vj, which is linear in N, larger than alpha G. Alpha G is sublinear in N. Okay, they have linear size neighborhood, meaning there's an edge inside. Done. You get K4. Which plus x1, x2, you get K4. Finishing the proof. Any question? Okay, as you can see, in this Ramsey-Turan problem, we also reduce the original problem on graph G, where we translate K4 freeness and independence number sublinear to the condition in the reduced graph that the reduced graph is triangle free and each edge weight is at most 1/2. Then it's very simple to derive this one by Mantel's theorem, which reflect back to what we need. Okay, if there is no question, I will see you guys next week.